Okay, it's 4:15 and we have a full session here, so we should go ahead and get started. So please continue to come in and take a seat. A reminder that the main cabin, the fasten safety seatbelt sign is still on, so you need to stay seated and not congregate in the aisles. In this session, I'll be joined by Komal Bali as a graduate student from the ETH Zurich, who will be monitoring Slack for questions. So if you're virtual today or want to just ask your questions through Slack, please do so, and she'll keep an eye on that. And the first speaker is Susan Redmond. Susan's in the optics group at JPL and is part of the Habitable Worlds team, contributing to both the integrated modeling team and also the testbeds team. So please, Susan.
Hi, everyone. Thanks for being here today. Everyone can hear me okay? Great. Okay. So I was going to talk about coherent differential imaging for habitable worlds, but seeing as we haven't really gone into detail about many post-processing techniques yet, I wanted to just take a bit of a step back and just go into how the way that we modulate the telescope, whether it's by actually modulating the observatory or the deformed mirrors, affects the our end-to-end ability to extract these exoplanet signals. I also want to highlight Natalia Sanchez's talk, which is on Thursday, that's going to go in a bit more into detail into a lot of different of these post-processing techniques. So we've seen this image a number of times already, but one of our main goals for habitable worlds is to be able to take one of these pale blue dot photos of an Earth-like exoplanet. And we also want to be able to take spectra of these exoplanets. And this is difficult for a number of reasons. And one of the main ones is that it's really difficult to distinguish planet light from starlight. And we heard about that analogy between the lighthouse and the algae. And we can break this down into a couple of different categories. One is the target brightness. So these targets in general, these reflected light planets, are very dim. And then you have to add in the fact that they're up to 10 million times dimmer than their host star. So that's difficult. And we also have our instrument systematics. And these can both be static and transient. So we've seen those static defects due to mirror polishing and things like that can create these speckles that look like planets. And then we also have the issue of the observatory drifting in time. So we have our mirror shapes changing in time, and that can introduce signals that are difficult to remove. And last, we have the astrophysical noise. So this comes from exozodi and dust and things like that. So we want to build an architecture that addresses each of these hurdles in a very holistic way. And to a lot of the themes that I'm going to touch on today will be similar to what Chris Stark talked about yesterday. And we need to look at what we're doing before we look at the target, while we're looking at the target, and also after we look at the target. And really kind of look at how all of these pieces fit together, because, as Chris mentioned, these incremental yields in different areas can really build up to a very substantial yield in science. So before we look at the target, we can do things like modeling the instrument, we can collect characterization data, and we've seen very good success in the web data in this regime, and also Roman plans to do this as well. We can also do something called looking at a reference star, which is also built into Roman's observing plan. So if we look at a star that does not have a planet, we can do speckle matching to try and figure out what's a planet and what's a star when we actually look at our target. This is going to be more difficult for habitable worlds because the angular size of the star is going to start to matter, and also the spectral type. So that's just something to keep in mind. When we slew to our target, we can do a number of different things. The first couple are we can modulate the observatory, so we can roll the telescope. So this is also part of Roman's observing plan. So the speckles field should stay in a constant frame with respect to the telescope, but the planet's going to move. We can also do something called target follow-ups, so we can go look at something else for a while, and then we can come back, and when we've come back, the planet has moved. But something to keep in mind with both of these is that as we're looking at this target, our mirrors are drifting, and so we need to be conscious of what that drift tolerance is to still be able to extract that planet signal. So another thing that we can do is perform real-time estimation of the residual starlight. So if we know it's drifting and we have this beautiful high contrast imaging instrument that can dig this dark hole, why can't we use those DMs to do other things while we're looking at the target? So that's where this concept of, for example, coherent differential imaging comes into play. So this leverages the fact that planets are mutually incoherent with their host star. And so that means that when you modulate those DMs, you are changing and moving the residual starlight speckles more than the planet. And we can do this and estimate the coherent electric field or the coherent aspect of that final science image. And using that, we can extract out our planet signal, since that should be the incoherent part of that. And this is going to be a really exciting option for Habitable World, since this already has all of that drift information baked in real time. It has all the stellar characteristics baked in, so there's no sort of matching to a different target that you have to do. Now, you might think, well, we have this estimate, like, why can't we do something with that? And that's the other thing that I work on, which is, why don't we just close the loop? So this is performing real-time estimation and control of that starlight. So while we're looking at our target and that wavefront is drifting, we use our nice deformable mirrors to correct for that in real time. And then we still have that estimate that we can do something with later on. So after we're done looking at the target, we can downlink all our data and hand that off to an analysis team. And there's a wide range of post-processing techniques that we can use to take kind of a noisy image like that on the right and turn that into a very high SNR planet signal. And it's important to note that what algorithms we have access to in that state are very dependent on what we've done in those first two steps. So what we did before we looked at the planet and what we did while we were looking at the planet. And choosing different options in those two stages can either exclude certain options or make them more difficult and make it either easier or harder to pair certain ones together. So we really need to look at this in a kind of a big picture way. So now that we have kind of all our options of what we can do at these three different stages, let's look at demonstrating something in the lab. So I work with the decadal survey testbeds at the Jet Propulsion Lab. So we have 2 high contrast testbeds in a vacuum chamber. We have others, but these are the 2 we're going to focus on today. And we can use them to test a variety of hardware and software solutions in a space-like environment. So this is a simplified optical layout of the decadal survey testbed downstream from the deformable mirrors. And we can get an image that looks like this. This is a half dark hole. We have a field stop in, so that gets rid of all the light outside of this D-shaped region. And that just reduces the dynamic range required of our detector, so we don't get bleeding into our dark region, because that would be really saturated. So when we go back to kind of our pre-target step, so in our pre-target step, we have a model of the optical setup. And then in this case, we're going to inject drift upstream. The DST testbeds are quite stable. They drift at about 10 to the minus 10 per hour. And we want to have more control over what drifts we're correcting for. So we actually inject some in so we can push the limits of the algorithm and see where it breaks. And we also have a model of the drifts present during the target observation. We don't assume that we know the exact drift that's injected. We just assume that we have some statistics on it. And this is a sample plot of what we get out of these types of experiments. In this case, the magenta line, that's our closed loop contrast. So that's with all the real-time focal plane wavefront estimation and control in action. And in the bottom right, we have the closed loop final image. And that blue line is the open loop. So that's if we did no correction with that drift injected. And I want to draw attention to these wavefront error numbers. So that's 56 picometers RMS that we've injected and 400 picometers peak to valley. So we're in that regime of that ultra-stable numbers that we've heard about. And hopefully down the road, we can improve this a little bit and maybe relax the OTA requirements and make Lee a little bit happier. So for our concept of operations or observing strategy that we've tried, we did a number of different kind of roll options. So we can either chop between 2 different roll angles, or we can do a continuous slew between 2 roll extremes. And we've injected a planet of about 1 times 10 to the minus 10 at different regions in the dark zone. I just want to note that we don't actually inject wavefront errors that are different associated with each of these different roll options. And what we've injected and corrected for is most similar to what you would see if you did that green line. But down the road, we want to be a little bit more strategic and realistic about what we're injecting and correcting for. So this is a plot of a variety of different post-processing techniques. Once we have taken all that data and put it through all those different concept of operations. And so this black line shows the best possible outcome. So in this case, if we inject a planet with an SNR of 10, we can recover a planet of SNR of 10. And there's two numbers that I want to draw attention to here. One is that our post-process 1 sigma noise floor is about 10 to the minus 12. It's about 6 times 10 to the minus 12. So that's on the order of what we think we will need for habitable worlds. And also that we seem to have a systematic. So we can see that it starts off as a line, and then we hit this elbow. And so that shows that we're hitting some sort of systematic in this analysis. And we think that this is limited by the DM probe commands that we're using. So but this is not a fundamental limit. So this is good in a way because it shows that we have this systematic, but we think that if we're just more clever about what DM probes we choose, that we can actually improve on this. I'm going to skip this slide just for time, but if you have any questions about arc fitting, this is a concept that I've been working on with Chris Stark. He generated these figures. I'm happy to talk about them after. Yeah, so looking forward, we're going to have the Nancy Grace Roman Space Telescope. So we're going to see a number of these options demonstrated by Roman, and hopefully with these advanced algorithms from the CPP, we can see some alternate ones. And then also there's a number of different test beds currently operating and also in development. And I think as someone mentioned earlier today, a lot of them probe different areas of the design space. And it's going to be important to be able to probe different versions of these observing scenarios, and also to make sure that we're injecting realistic wavefront errors when we try and do these big end-to-end observing scenario simulations. So yeah, thank you, and if you have any questions.
Great talk. Questions for Susan?
Hi, Svetlana Berdugina, Switzerland. A short question. Thank you very much for presentation. How do you choose the roll angle? Is there constraints on that?
So right now we are operating in the magical regime where we can have any roll angle that we want. Obviously down the road that's going to get more constrained, but we wanted to start off kind of being flexible and then narrow it from there to see how much worse things get when we start narrowing that regime.
Lee?
Yes, Susan, when you were showing the post-processing methods you looked at combining it with, have you looked at what J.B. Rubio talked about this morning, the spectral post-processing? And do you think that if you did the pairwise probing while you were doing, a medium resolution spectra, that you might get more information out that would be helpful, and then you could just bin it up if you needed to?
Yeah, so we haven't looked at that yet. A lot of the runs that I've done, obviously DST time is valuable and limited. And so a lot of the runs that I've done for these, that run I showed there takes about 30 hours wall clock time to do. So then when you try and add in multiple wavelengths, then that's 3 days if you want to do 3 subbands. Generally we try and do 5. If we had an IFS and we could do those all at the same time, that would be amazing. And having that extra data would be awesome, and it doesn't change. If we have an IFS, it doesn't change anything about the algorithm. So we're using an EKF in this case and not the pairwise probing, so we just need 1 image per iteration. Yeah, but it doesn't change the overall algorithm if you use something to extract out those monochromatic images. So yeah, we would love to do that. And I think Epic 5 eventually down the road will have an IFS, and then we'll get to test those out.
Great. Let's thank Susan again. Okay. Yeah, the next talk is by Rodrigo Ferrer-Chavez, and Dimitri McElwain was advertising for this talk, calling it very tantalizing. I'll be talking about AI and using that for post-processing, so really looking forward to this one.
Okay, can you all hear me? Okay, thank you so much. Yeah, so I'm hoping you will find this tantalizing as well. Yeah, my name is Rodrigo, and I'm going to be sharing some work we have been doing on image processing for high contrast imaging. And the basic thing I want to argue is that if we're going to send a super advanced hardware instrumentation telescope into space, we should also accompany it with like the most advanced processing that we can have for it. So now, by now it is clear that it is going to take a lot, to get something like this from our telescopes, out of advances in instrumentation, in hardware, and all those things. But as Susan very nicely pointed out, we also need to think about post-processing. Actually, I like Susan so much, her talk, that I'm going to use a figure from one of her papers. So what you see on the left is basically a sample high contrast observation, before processing, and on the right is after processing. So you will see, I really like this comparison because you see that on the left, whereas instrumentation is fantastic at creating this dark zone, of higher sensitivity, if you do not post-process it correctly, you would never see the planet that was there all the time, Like observations do not come with this suspicious, green circle. So what I want to show now is that what this looks like on real data, and I'm going to be showing I'm going to shamelessly plug some of my work in JWST. So this is part of a program that I'm a part of, trying to find sub-Jupiter mass planets with JWST NIRCam, and this is a real observation that we took from our survey. What you see here is also an unprocessed image. This is what Starlight looks like. This is what we have to remove. So after we apply our state-of-the-art methods for Starlight Subtraction, we end up with something like this. So we see that we did indeed remove a lot of starlight, but there was also a lot left. And it might not look like a lot, but planets are faint, So if you want to find them, you want to make sure you can push as deep and as faint as you possibly can. It would be a tragedy, I think, if you were to build the most powerful telescope in the history of humanity, and then you measure Earth, and Earth is actually there, but you cannot recover it because you have a lot of junk on top. So it would be comically tragic, I think, So why does this happen? Why are we not able to remove all the starlight that we can? The point is basically what the image processing that we use now looks like. So we use basically reference images and principal component analysis as the state-of-the-art practice in our field. So here we have a science observation, right? This is where we want to search for planets in. In addition, as Susan mentioned, we will take some reference observations, right? We might take maybe an observation of a different star or of the same star at different roll angles. And then through PCA, you will build a starlight model, which you can then subtract, and you hopefully find some bright planet looking at you, or at least a clean scene where you can rule out the presence of planets. So the fact that this is built on reference images tells you that there's going to be some fundamental limitations. First, the telescopes are unstable. Even in the most advanced, most stable telescope possible, you will never get rid of all stability, which means that by the time that you take your reference image after your science image, your telescope state will have changed. So even if your scene is exactly the same, your image will not look the same. And you cannot build a perfect model out of imperfect references. And this instability is also what causes these dark zone regions to degrade over time. I will come back to that in a second. And secondly, PCA is a merely physics, maybe data-driven method, right? It ignores the physics of image formation. And we know a lot of information about the physics, right? We know that when we PCA these images, we're not PCAing images of cats, right? We know that what the design of the optics are, we know what the spectrum of the star is, we know data from wavelength sensors, we know a bunch of things. So this is a big opportunity to build all this information and actually overcome telescope instability, so at least compensate for them partially. Now, I think a promising way to combine these 2 points is to look at what the AI community has been doing recently. Now, this is also like a shameless plug because both of these papers are from our collaborators in this project. But we have seen in recent years, right, what AI-based, physics-based imaging can do, either in images of black holes or in images of butterflies through turbulence. AI is a way now, and machine learning and all these techniques are a way to build in more physics into our algorithms instead of substituting the physics that we could be using. So what I want to show now is how this can be applied. And this is, again, another shameless plug. I'm going to be showing the example in our own work. So our starting point is that starlight residuals are basically a matter of uncorrected optical aberrations. So the most natural way to start is to try to solve for these aberrations, what aberrations are actually happening in the telescope. So the most naive thing you can do is something to try to model them, right? You have a coronagraph model, you have maybe a recent wavefront sensing measurement, and you model what you think the starlight looks like. You may not get a great fit, but you can then compare with your data and optimize the free parameters in your model until you get a good fit. So this is extremely obvious, right? Why do people not do this? Well, because your optical system has millions of free parameters if you want to get a really good fit. And this is something that you cannot just optimize with, SciPy.optimize or with MCMC or something, It might take forever or worse, until HWO launches. So what we want to do is to look at people that actually train these kinds of models all the time. We call them neural networks. So how do they do it? They leverage automatic differentiation. If you code your model, any model, in a way that you can compute analytical derivatives through it, you can optimize all those parameters in pretty much no time, at least compared to the usual methods. So what we do is that we code our coronagraph model or optical system in a way where we can compute these derivatives and make use of backpropagation, GPU-based optimization, and these things. And the computational challenge pretty much goes away. Now I want to show how this works. First, I'm going to show some work with the simulations. This is, again, a simulated image, right? We can simulate a PSF, we can inject a planet, and we can see if we can recover them, pretending we do not know what aberrations we injected. And we can. This is what the optimization looks like. And that blob is the planet, of course. We also show in a proof of concept paper from earlier this year that our method surpasses very systematically and significantly PCA-based methods, what you can see on the left compared to our performance on the right. And this 10 to the minus 6 simulated contrast, it doesn't seem like a lot, but for JWST, that is very hard work. It is like really trying. That's about as best we can do. But this is, of course, only simulated data and very simplified simulated data. So can we do better? I'm going to show now some examples from a paper I have in progress, also applying all these methods to the JWST surveys that I've been working on. You may remember this image from a few slides ago, right? You will see how using PCA did not get us all the way to what we can do. All of Starlight was left. When we apply our own method, we get a subtraction that looks like this. So there are still some systematics, right? But you can see by eye that it is a lot better. It's a factor of several better. We find no planets, sadly, but at least we can get better upper limits in what our image looks like. But this is a more interesting example, I think. This is a real new planet candidate that I found analyzing our surveys. We can talk about the candidate later, right? But the point is that we have several reasons to think that this is probably a real candidate. And you can see that PCA with some 100 reference images can get a pretty solid detection at something like 9 sigma. What we get with our method is something almost double the SNR. You can even see the airy rings around the planet. And on top of that, this was done with our model that only takes around 10 minutes-ish to train on a single GPU and not a big cluster, and without needed 100 other reference images. So this is pretty nice. I want to comment on another thing. As I mentioned before, this is a fully physics-based method. So what that means is that when we solve for our Starlight model, we, for free, get also an estimate of what the telescope aberrations look like. So I want to comment very briefly on this. One example of an aberration we might fit for is, for example, phase aberrations at some plane of the telescope. When we apply this to several targets in our survey, we get something like this. We can say a lot about this, and you can see how the LEO stop, you can kind of see the shapes of it because that's the only part of the light that actually influences the PSF. But what you see is that across different stars, across different observations, there's a very similar structure, which means that this is pointing us to a real systematic error from our models compared to our actual telescope. So this is something that we can really make use for when we try to optimize for what can be going wrong in our telescope. We can use this to characterize what is going on during our observation. We can use this in a testbed situation to see, if you're not getting quite to 10 to 10 contrast, you do maybe this framework and you see, okay, what could I tweak? Or you could use something like this to at least partially compensate for drifts in the telescope that cause dark holes to degrade. Now, I want to finish on one last point. These two subtractions that I showed are both, again, pretty impressive, but we have to stop our iteration process at some point. That is because our model has so many free parameters that if you just let it run unconstrained, it will end up, fitting even real signals. So we have a dedicated stopping condition to prevent that from happening. What I want to show is what happens when we relax that condition. What does the fit look like when we just let it run unconstrained? And it looks like this. There's an image where we have removed pretty much all of the starlight that was there. Almost no speckles to be seen. And all that you see here, just realizations of fundamental noise. Now, this is very exciting, right? Because this is real data. This is real data from JWST, and we were able to find this kind of solution. And when I sent this to Jason Wang, on Slack, he told me this. Because PCA has never been able to do something like this. So, and us as they're working on it, for like a year and a half or something, we can get something like this. Again, this is still not controlling for overfitting, so there's a lot of work to be done. But I think it shows the promise of what you can gain when you combine your knowledge of physics with state-of-the-art instrument models and instruments and actual advances in computational imaging. So hopefully this will turn into an image like this in the future, or it might be at least a step to get there. Now, I could just end here, and I think I will. Thank you.
Very tantalizing. Any questions from the audience? All right, we have a number of hands. Did you have a hand or you?
I did.
Okay, yeah, okay. We'll start with Janice.
Could you say a little more about the models that are being used, and are they neural networks or?
Yeah, the model itself is something that we take, from some model that is publicly available. So our starting model for the Fourier optics models that are available in something like WebPSF or STPSF. And from there, we get, the mask designs, the wavelength dependence, some chromatic aberrations and all that. And then after we have that in place, we simply optimize it as though it were a neural network, if you like. So if a neural network does, I don't know, like for a modeling pass or something, our pass would be something like multiplying the electric field by that mask. And then the derivatives are tracked through that operation.
Great. Dimitri? Actually, Komal, can you pass the microphone back?
Oh my God, oh my God, oh my God. This is amazing, amazing work. So you mentioned overfitting as an issue. Can you develop this a little bit more? So what is your stopping condition? What's the catch? I want to understand that more.
Yeah. Right now, the catch is that right now our stopping condition is empirical. So when during our fit, and you see, like the video simulations, we actually inject a fake planet somewhere, like near the center, with a known flux, and then every iteration we track it, right? And what we usually find, depending on where we inject the planet, regardless of where we inject the planet, is that the SNR of the planet kind of goes down and then goes up and then goes down, right? So our stopping condition is like, okay, whenever we see that the SNR is starting to go down, then we stop, But I think there's a real interesting work to be done, like more fundamental systematic ways, I suppose, to avoid this.
A question in the gallery?
Yeah, very exciting work. So I wonder, do you need to retrain or re-optimize your model for each of the observations, or you can optimize once and apply to many different observations?
Right. The thing is that every observation, and that is pretty much the fundamental issue, right? Has different aberrations happening when they happen, right? That's why you cannot just subtract one from the other and get a perfect match. So even though we could, say, calibrate our models on, a bunch of different stars and then just, do a little delta on top, you will have to do that delta on top, right? Because the aberrations in the telescope are not the same that happen all the time.
We have time for one more question. Chris, sorry, Mike, you're going to have to hold yours until the reception.
Thanks so much for the great talk. This is super exciting. So I have so many questions. So I assume since this is model-based, you're not adding any Poisson noise then during the subtraction. And is this telemetry free as well?
Well, we use the wavefront sensing data that we do have, So in the case of web, for example, if we observe an image, on Thursday and we have wavefront sensing data from Wednesday, you might use that as an initial condition. But other than that, we just model it, and we have talked a lot about, other telemetry data we can use to aid this model, but right now it's not something we're doing.
All right. Let's thank Rodrigo. Oops. Okay, the next talk in this session will be from Bertrand Mennesson at JPL, where he's the Habitable Worlds Observatory pre-formulation scientist at JPL and the Roman Coronagraph science lead.
Thank you, Mike. Can you hear me all right? Yes. Yeah, delighted to be with you all today. I have the privilege of working both on the Roman Coronagraph, so the near-term future, and HW, the slightly longer-term future. And so that allows me to talk to you today about both the HW and the Roman coronagraphs, and try to better understand how they might relate to each other, connect to each other, and compare with each other. So as we know, the Roman chronograph in a nutshell is a visible light, high contrast technology demonstration for HW. It will be the first space-based chronograph with active wavefront control. It has 3 observing modes: broadband imaging, polarimetry, and spectroscopy. For spectroscopy, it will only use a point source spectrograph with a slit at a resolution about 50. The requirements are fairly conservative for Roman in terms of technology requirements. We are only asked to provide a detection limit for a point source of 10⁻⁷ relative to its star at a separation of 6 lambda over d for a single photometric band, which is about 10% in bandwidth. However, we designed the instrument to largely outperform that requirement. That's been evidenced by the test that we ran at JPL about a year and a half ago in vacuum. So TVAC was very successful with actually the demonstration of these requirements with flying colors. And I'll get back to that in a few minutes to tell you more. So the chronograph on Roman includes most of the key functionalities and subsystems anticipated for HW. That includes ultra-precise wavefront sensing and control, a pair of large 48 by 48 actuator deformable mirrors, high-contrast coronographic masks, ultra-low noise photon counting detectors, in that case EMCCDs, which are used for 2 of the cameras on Roman chronograph. And then the ability to really test, at least on sky, at very high contrast for the first time, some of these high contrast data processing techniques that we just heard of, namely using ADI and RDI, so angular differential imaging by rolling the telescope, and referential differential imaging by using data on a reference stars. The only exception is that we will not have multi-planet spectroscopic capabilities with Roman, and they will be required for HW, and we anticipate that behind the chronograph in HW, we will have a multi-object spectrograph at least, or even better on IFS. And of course, all of these technologies need to be working together as a system for the whole high contrast performance to be delivered. So this is a schematic layout of the instrument for the Roman coronagraph. And you recognize here the low-order reference sensing camera, which is an EMCCD. The high-order reference sensing camera, which is also our science camera, which is being used also for high-order reference sensing. And then some of the control systems for active wavefront control, so the FSM, the fast steering mirror, the focus control mechanism, and that pair of DMs that can control both amplitude and phase broadband. And then we have a large variety of focal plane masks and pupil plane masks, so different types, different flavors of masks that we can switch from. I think that's important also to retain for HW that we actually have these large wheels with different masks. I mean, for HW, we're going to be looking at a variety of stars at different distances with different types of planets. We may want to also be resilient to different operating conditions. So I think it's interesting to also have this ability to roll in different masks optimized for different science or actually delivered performance on sky. There's a lot of different configurations. I'm not going to go through all of them. I'm just going to mention 5 of them here for you, which are some of the main ones that will be provided by the Roman coronagraph. They differ in their central wavelengths, the bandwidth delivered, also the type of dark hole that we generate, the extent of the dark hole, and then the type of coronagraph being used. Once again, 2 main flavors. The hybrid Leo coronagraph, which is a focal plane coronagraph, and a shape pupil coronagraph, which is a pupil plane coronagraph. So it's kind of interesting because we can try these different approaches, understanding their pros and cons. They are sensitive to different aberrations or instabilities. It makes us pretty resilient to different conditions. In the lab, in TVAC, before delivering to our friends at Gaudi, we did test 2 of these modes and showed that both of them actually did meet the requirement that I mentioned earlier. So we only had to do it for 1, we did it for 2. And I should also highlight that these final contrast performance levels were not limited, we think, by any kind of hard physical limit, but we had to stop because of the time allocated in TVAC, and we prefer to actually test two. I want to show that two pass requirements rather than push for one indefinitely. So where are we standing now with the Roman Space Telescope? Well, we are getting ready for a launch, which is in 15 months, nominally. As I said, the chronograph was delivered in the spring of 2024. Late last year, followed this beautiful telescope. Matt talked about it this morning. It's really a thing of beauty. If you want to go see it, it's not too far from here. It's now been integrated to the Coronagraph and the rest of the payload instrumentation and the spacecraft. And all of that assembly is actually now in the chamber for TVAC, for testing. The chamber is still open, but the TVAC testing, which is going to be 2.5 months long, is going to start in a couple of weeks. And so within a couple of weeks, we'll have finalized all of the TVAC tests of the overall telescope assembly, observatory assembly, I should say, and verify the optical performance end-to-end. So switching gear a little bit and talking really about HW and how these two coronagraphs on Raman and HW may compare. You ask, what's the technical relevance of Raman to HW? And to answer that question, we use that usual figure of merit plot that every coronagraph uses, which is showing the planet-to-star flux ratio or point source planet-to-star flux ratio that you get on the y-axis as a function of separation. And as we know, most of the state-of-the-art telescopes in space and from the ground at the upper right corner of this actually reside in this region here, which has a contrast of the order of 10⁻⁵, maybe 10⁻⁶, at separation of 0.5 to 1 arcsecond at visible to near-infrared wavelengths. And eventually, with Raman, we want to demonstrate that type of performance here. That's our requirement. What we think we're going to be doing is significantly better than this requirement. What we demonstrated in TVAC is that we are below that line. So if I were to guess, I would say that the performance on Sky will fall somewhere in that yellow region here. So I think it's fair to say that our predicted detection limit is 100 to 1,000 times better than the state-of-the-art from ground and space at the same wavelengths. Depending on where you fall in that zone, you're going to be closer to 100 or to 1,000. Yet we are still a factor of 10 to 100 away from where we need to be for HW for these Earth-like detections. But the important point, which came a little bit as a surprise when we realized that, when we kind of were working the requirements for HEBEX at the time and those of Raman, is that the requirements of the subsystems are fairly similar. So in fact, most of the functionalities and subsystems on Raman have predicted performance, which are in family with what would be needed of HW. So how is that? It's kind of surprising. But the reason for that is simply that the performance of the Raman coronagraph is not limited by the coronagraph itself, nor by the exquisite quality and stability of the telescope, but rather by the aperture, the entrance aperture of the coronagraph. The telescope itself, which is as an entrance pupil, which is really unfriendly to coronagraphy with these large struts and central obscuration. So in other words, if we are able to get to 10⁻⁸ better than 10⁻⁸ detection limit with the Raman coronagraph, we think we have a good shot at getting around 10⁻⁻ detection limit with a more friendly aperture like we envisioned for HW. So in terms of science, we will probably just skim the top of the giant exoplanet population around mature stars. And you can see that here we are predicting to be close to the flux of an exo-Jupiter. But in some way, that also means that it's going to be a huge region of unexplored parameter space, even after the Raman coronagraph, for HW to tap into. And that's something we should not forget when we talk about HW. I'll get back to that. In terms of science, still, I think that one science case that is close to my heart, and we'll talk more about it during the panel discussion, is this fantastic machine at HW that Raman will be for conducting exosolic surveys in preparation for HW. So that science case is pretty resilient to performance of demonstrated on Sky, and it's kind of almost a given. The HW coronagraph, science and architecture exploration, we are there right now. We are really in the early phases of trade explorations. So we're still capturing really the full breadth of exoplanet science objectives. Among them, we've heard a lot about exobiology and the exploration of whether Earth-like planets exist with biospheres and are common or rare in the galaxy. We also want to explore the concept of habitability at large, which means like it could be that some particular planetary architectures are more prone to having habitable planets in their inner region than others. We'd like to understand that. But something also we should not really forget is that HW is really designed to test the habitable zone concept. It's still a concept, it's still a mental construct, and we know that with a mission like HW, these are actually old simulations for HABEX, but with HW it's going to be the same thing. We're going to get a lot of smallish planets detected. Only a few will really fall in that nominal habitable zone region, and that's where we're going to get a lot more planets very close to that region with slightly larger separation, slightly larger sizes. And that's exactly what you need to understand that concept of habitability. Is this planet habitable? Is that one habitable? No, that's what this mission will explore. And it is getting even more interesting that we know there are, at least at small separation, an abundance of these slightly larger planets, for instance. Are there super-Earths? Are there sub-Neptunes? We don't really know. They have a large variation of densities in that range. So we don't really know what they are made of. There were some talks yesterday about these mysterious planets. We're going to be finding a lot of them. We're going to do spectroscopy of them to try to understand what they are made of. And guess what? They're going to be even easier to detect than an exo-Earth because they're going to be larger. They might have higher albedos. And they may also have more extended habitable zones. So I think these are very, very interesting targets for us. And the point I'm trying to make here is that, yes, we should design this mission to do exo-Earth observation exactly like Earth 2.0. That's good to anchor ourselves to this type of planets. But it shouldn't be at the expense of these other planet types that are going to be a lot more numerous and in our sample, and possibly equally interesting. Getting back to the comparison between the HW and Raman coronagraph, we talked about the difference in detection limits already. There's the desired wavelength range, which is going to be very different. The Raman coronagraph is about 0.5 to 0.9 micron, 0.875. For HW, we'd like to extend that at least to 1.7 micron in the near infrared, and possibly down to the near UV to look for the ozone cutoff at even lower abundance of oxygen than in modern Earth. Multi-object spectroscopy, I think, is a must. We're not going to spend hundreds of hours getting the spectrum of a single planet with HW. And similarly, there's probably going to be a few building blocks similar to the Raman coronagraph that we're going to be using in parallel, because we're not going to get spectra 20% at a time. Sequentially, we're probably going to want to have a few parallel channels split in different wavelengths. So maybe 2 or 3 such coronagraphs. Finally, looking at some of the key architecture traits that we have been starting to do across the community and the project office for HW, we looked at different aperture types. That's the first thing you want to look at. Based on the Raman experience, we know that the main performance limitation from Raman was coming from the influence aperture, as I just said. We could not change it, so now we are finally free to co-optimize the whole system, the telescope itself, the aperture, and the coronagraph. And so we've been starting to explore these different apertures. That's the so-called ESC 1, 2, and 3, which are shown here in scale relative to the Raman aperture. And 4 and 5 are also going to be explored with slightly different types of segmentation and aperture sizes. Not going to have a lot of time to go through this. Other architecture traits that we are looking at, different masks, optimizing masks per aperture type. That's something that Ross talked about earlier. There are traits between different coronagraph performance parameters, which are degenerate. We're trying to understand that space as well to make our life easier if possible. We're trying to see whether we can indeed cancel Starlight very effectively behind dichroics, or whether we can do this with both polarizations at the same time. Last thing I want to mention is this idea, this trait about spectral resolution. I think that's one of the main things that is kind of new since the old TPFC days when people, for people who were there at the time. And we're still considering nominally a resolution of about 100, but that's ignoring a lot of recent developments from the ground and even more recently in space. So on the ground at Keck and VLT, high contrast observations have been obtained at medium to high spectral resolution. We've seen this morning the fantastic results on web that Jean-Baptiste Ruffiot showed that show very strong physical information can be retrieved at higher spectral resolution. That's all for bright self-luminous planets in the near-infrared. Can we extend that to fainter planets seen in reflected light? I think that's a question worth asking. I'm not saying we will necessarily do this, but we should make sure not to leave any kind of information on the table. And by that I mean we should work at the spectral resolution, the maximum spectral resolution we can get without being detector noise limited, and nothing lower than that. That's a notional layout for the Coronagraph we're considering for ESE4, just to give you an idea of where we are. You can see that beam splitter here, that dichroic that splits the light between two different channels that observe in parallel. One that can feed a broadband imager, short of 650 nanometers, and IFS at longer wavelengths. And at the same time, you can observe north of 850 nanometers, choosing sequentially between IFSs and broadband imagers as well. So that's kind of like where we are right now, and it could, of course, change. So takeaways, the Roman Coronagraph instrument is fully assembled to the observatory. It's preparing for launch by October of 2026 on cost and schedule. Roman prepares both technologically and scientifically for the HW Coronagraph. I want to advertise here a white paper call, which is on a street that has been issued about 2 months ago that's calling for ideas for the community for observations with Roman. So in particular, if you can think of some that will inform HWO, please submit a white paper by August 7th. It's clear that further progress of our Roman and Webb in terms of coronagraphy will come from the joint optimization for the first time of the telescope and the coronagraph, and by having both actively controlled, not just one of them, and that's called HW. To finish, we are exploring HW architecture trade space through a detailed analysis of coronagraph performance versus a number of high-level design parameters, so that's ongoing. HW will be designed to search and characterize Earth 2.0 in different stages of its biosphere evolution. We know that. But once again, I'd like to insist that HW will generally transform exoplanet science and comparative planetology, at least when it comes to observing mature planets around sun-like stars. And I thank you. I'll take any questions you have.
Questions for Bertrand? Yeah, maybe it's in the interest of time. We'll start the panel discussion, and I think Laurent is planning to have some time for questions and answers then, so people can think about it. So let's thank Bertrand again and invite the... So now we'll have another panel discussion. This panel is on Roman as a Pathfinder panel, and it's been organized by Laurent Pueyo and Bruce Macintosh. So thanks to them for preparing that. And Eva Laginja will be moderating this panel. Eva is at the Paris Observatory as a Kness Fellow and is part of the Roman Coronagraph Community Participation Program team.
Thank you, everyone, for being here for this panel. It is the last activity of the day before we have the reception after. As we have just heard from Bertrand, Roman will fly some key technologies that will be in space for the first time. So it will be the first space telescope flying a DM-assistant chronograph. At solar system scales at about 5 AU, Roman will probe 100 to 1,000 times deeper than Hubble. With that, it will also be the last space telescope to fly some of these technologies before the launch of HWO. And as such, it will be invaluable for both the technology and the science readiness of HWO. On our panel today, we have Feng Zhao from JPL, we have Scott Gaudi from the Ohio State University, we have Bertrand Mennesson from JPL, we have Brianna Lacy from UCSC, we have Bijan Nemati from TELUS, and Alice Liu from GSFC. Let's first look a little bit at the big picture. So Feng, you are the project manager of Roman, and you've been with the Coronagraph for its entire life. Beyond the flight demonstrations of the key technologies, can you explain to us why the work done over the past 10 years will save us some valuable time for HWO?
Oh, thank you for that question. I think the best asset we have from the Roman project to HWO is a very experienced team. You heard from Lee, day one, talking about empire building was built in the 30s. Why? Because the experienced crew built buildings around it. I think this is the right time for a Roman team to take on a new challenge for HWO, and that will help us to save the money.
Yeah, so it definitely will be very important to also scale the milestone that will be there for HWO with the money that you just mentioned. So if we switch gears a little bit and go straight into the science, so Roman will reveal the giant planet zones of a couple of our nearby neighbors. Brianna, you are an expert in the modeling of cold exoplanets. How is this going to help us to place solar system architectures in context for HWO?
Yeah, I really liked Bertrand's phrase of skimming the top of this population. As you said, just a couple of these will be accessible of the most favorable targets, but it's still really, really exciting because it's the first time we're going to see true analogs to the solar system planets in reflected light. So I've included a little scheme here in the center middle where you can see the planets that we've been able to characterize atmospheres so far are really those hot Jupiters that are really close in, and the directly imaged planets in the near infrared that are very far out, more like greater than 10 AU. And those are interesting, but they're kind of weird. They're not our normal giant planets. And so with Roman, we're finally getting a look at those true analogs to solar system planets. And with the wavelength coverage we have, you're sensitive to what clouds are present, how high up or how deep they are in the atmosphere relative to the absorbing gas above, and maybe if we can get a spectrum, maybe a methane feature. So it's not the panchromatic that someday we'll hopefully do with HWO, or not panchromatic, but higher signal to noise, more resolution that HWO can do, but it will give us that first look, and I think that'll give us a really valuable chance to test and practice how we might do some of the trade-offs with how to interpret this, of maybe needing to look at different phases and how to make sense of a different type of observation than we've seen before.
Yeah, certainly. And this has also been said in one of the panels yesterday, where it would be short-sighted to sort of skip this space in between what we can do now, what we will be able to do in Roman, and go straight to HWO. So having even a little bit of that, or even a little bit more, is going to be very, very valuable. And so to enable this type of science, there are a couple of critical engineering questions, obviously, that will need to be addressed. And we know that one of the key questions before the JWST science operations was whether or not the telescope thermal behavior and also the optical stability, like how they would match the pre-flight predictions. So I'm turning to Alice. You have run the modeling team for Roman, and you are now running the one for HWO. Can you tell us how the HWO chronograph builds upon this NASA heritage?
We have learned so much from JWST and Roman modeling experience. I'll highlight two key lessons that we plan to take forward to HabWorlds. The first one is about building an efficient systems analysis process. We started the process that was built by JWST. They gave us a strong foundation. And then the Roman team greatly improved the process by building more effective tools and process and automating the process as much as possible. So with this capability, we can then evaluate performance and design impacts to performance at a much faster pace. On HWO, we'll be using these tools. In addition, we'll be expanding these tools to include various control systems, including control systems for thermal management, for pointing and line of sight control, for wavefront sensing and control, for segmented telescope, and also for the Coronagraph deformable mirror. So this capability will allow us to choreograph all the different layers and stages of control system until we finally meet the ultra stability that's required by the Habitable Worlds Observatory. And then the second idea is the idea for model as you fly. This is a term coined by Gary Mosher and Marie Levine on JWST. As we build larger space telescopes with more stringent stability requirements, test as you fly or test verification may not be feasible. Fortunately, with JWST's great on-orbit performance and the Roman model validation efforts on the ground, we were able to demonstrate that these engineering models can predict the behaviors of our complex systems. So this gave us an opportunity to think about how we do system verification, what tests do we do on the ground to check workmanship, functionality, and what tests do we do to validate our models, and then rely on these models to help us verify performance requirements in the flight environment.
Yeah, so what I'm hearing is that, in particular, doing all of these things for Roman will give us the confidence that going from one of these large telescopes to the next and towards HWO, we can really fully exploit the lessons learned from previous missions. So let's take a step forward and go from giant planets to smaller planets, and from doing one star at a time to doing surveys. So the goal of HWO is to fully explore at least 100 nearby habitable zones in possible solar system analogs. Scott, can you highlight a couple of key demographic insights that the Roman Wide Field Imager will yield? How can NASA optimize HWO's architecture and target selection?
Thank you for the question. Yeah, you may have heard that Roman will actually have a wide field instrument as well. And one of the core community surveys to be carried out with that instrument is the Galactic Bulge Time Domain Survey, where Roman will stare at the galactic bulge about 1.4 square degrees for about a total of 430 days with a cadence of about 12 minutes. And with that data set, we'll detect thousands of planets with the gravitational microlensing technique and maybe of order 100,000 transiting planets. And we'll fill out the parameter space, as you can see in this plot here, by Robbie Wilson, and we'll be sensitive to basically any planet with has mass or radius greater than twice that of the Earth at separations from 0 to infinity, including free-floating planets, around all the major galactic populations, including the thin disk, the thick disk, and the galactic bulge. So this will be the ultimate kind of statistical census of exoplanet demographics that we have. And it's going to address some important questions in demographics, as you asked, that are very relevant for HWO. So as we know from the great review by Vicky Meadows and Barnes, you know, in order to understand habitability, we can't just take a spectra and hope that we can say, okay, this is a habitable planet. We're going to have to understand the context of that particular planet. And that means understanding the planetary system that it lives in. And Roman is going to give us that context. So just a couple of questions that we might want to know in order to help interpret the spectra that we get with HWO. For example, what is the frequency of small rocky planets at larger separations? We know that frequency at small separations from Kepler and TESS, but it may very well be that those planets have been sculpted by the harsh radiation environment that they live in, and so they may not be representative of the planets at larger separations in the habitable zone. There's also the fact that most habitable zones in stars are located interior to where the snow line was in the protoplanetary disk. That means they formed mostly dry. That means water had to be delivered from beyond the snow line. And in our solar system, we think that was asteroids and comets, but we know that the large planets, Jupiter, Saturn, Uranus, and Neptune, played a vital role in delivering that water, very likely. That could be true in other planetary systems as well. So we need to know what's out there to deliver the life-giving water. And also, Roman has some sensitivity to Earth-like planets in the habitable zone of their parent stars with the microlensing technique. It's not great, but it will certainly help the estimate of Eta Earth that we've gathered from Kepler.
Yeah, and so I believe also that these Eta Earth estimates have been mentioned a lot, in particular yesterday, and so there will be some things that will be directly informed by Roman. I would like to come back to tech. Bijan, so you are the brain behind the Roman aero budget. And you are the one who knows where the tall poles are when seeking for exoplanet imaging in space. Based on your experience, which technologies would benefit from early significant investments? What's essentially the best bang for the buck?
Well, I would say that there's 2 or 3 that come to mind. With detectors, I think that if we're doing direct imaging, the EMCCDs that we developed for Roman improved a bit, would be fine. But once we go into hyperspectral imaging, like an IFS, that same light that fell on 1 pixel will fall on 112 pixels. And now we are in extreme need for detector efficiency and low noise. Furthermore, when you think about how you model a thing like a detector, you think, well, what's a detector? It's a source of noise and lack of efficiency. And that's all correct. And then you put in there basically parameters for these things. But subtle things like the non-constancy of patterned noise ends up limiting lowered wavefront sensing. It was in a sense an unpleasant surprise how vulnerable we were in the not so fixed pattern noise of the detector. And so those details will matter quite a bit. Other areas that everybody knows quite well about is that deformable mirrors are going to be a challenging thing because whereas our deformable mirrors and our ConOps work just fine for what we have to do, we will have to worry about ceramic technology, deformable mirrors, drifts. And if we try to solve that or kind of circumvent that saying we're going to go to MEMS, then we have to solve the corrugation of the wavefront. So those are significant questions to ask. I would also say that speckle stability or any form of speckle estimation error is going to be huge. But of course, it's very, Rodrigo's results were extremely exciting. So, but clearly we all understand that that's going to be a significant issue.
Okay, and these are also things that Bertrand already alluded to. And as we've seen throughout the 2 days, is really also areas that have this deep investment because they have been identified, and we will learn even a lot more once Roman comes to leverage that knowledge for HWO. For observations, so exozodiacal light is supposed to be a big source of noise for HWO, and Roman will be the prime facility to observe exozodi at concurrent spatial scales. So Bertrand, you have been thinking about this problem for over 30 years. And so as we mature the detailed architecture for HWO, now is a good time to use that experience, I believe. Roman will become a very important asset to anchor our choices when thinking about these things, but anchor the choices with astrophysical measurements. So can you share how you would go about building the most informative experiment for this? Would it be a couple of very deep exposures with Roman, or would it be a larger sample with Roman complemented with other observations like with Hubble and JWST?
All right, yeah, so thank you for the question. Yeah, I've just been thinking about it. I don't have any answer, but so seriously, so there's been considerable efforts, right, to measure exozodiacal light at mid-infrared wavelengths with KEK first, and then with LBTI the last decade. So there's been a lot of measurements in the mid-infrared. We've learned quite a bit. We've learned that exodi is probably not too much of a problem, but there's still quite some uncertainties. And the biggest uncertainty of all is that we don't have any visible measurements. So we don't really know, it's kind of difficult to extrapolate from mid-infrared measurement in thermal emission how much scattered light we're going to see from exozodi at visible measurements, so at visible wavelengths. So the next frontier is really visible measurements. I don't want to discourage people from trying to do better a little bit at LBTI and observe with JWST. JWST will not have at mid-infrared wavelengths the necessary resolution, but my colleague John Debs tells me that we might be able to do some SCD fitting and still find some excesses at mid-infrared wavelengths. There's also an instrument at the VLTI called NOT, which is going to do a 4-micron survey of exoplanets, but also exozodi that could be useful. But I think the next frontier is going to be with Roman. For the first time, measuring the level of exozodi at the wavelengths of HWO is going to be really crucial in order to prepare for HW. And I've prepared just a slide here that tells you what we could expect to do with a survey. So probably what we would do is we'd do a first small program with a small sample of 3-4 stars, some with exosody measurements and detection, some with clean non-detection, so we can exercise the instrument and anchor the models of visible to mid-infrared conversion. But then after that, if that's successful, we could actually do a pretty sensitive survey of exosody with Raman. So if you look at the plot on your left, you can see as a function of the inner working angle of the coronagraph, how many of the HWO typical targets we could access within the habitable zone. And what it tells you is that if you can work at short of 0.2 arcsecond, you can probably survey 50 of them inside the habitable zone. And you could probably do that on the right side with a cumulative observing time of 10 days. So that needs to be recomputed. That's from like 3 years ago. We have a new HWO target list. We have better performance IDs for Roman, but that's the type of survey that I would dream to see happen in an extended phase.
Understood. Understood. Thank you. We do have a little bit of time, so we would like to take some questions from the audience. We have microscopes, microphones, telescope, microscope, microphones. It's all kind of the same thing. Microphones in the room. I think, yeah, Susan.
Awesome, thanks. Bertrand, this is for you. I was wondering if you see any place for experiments like the Picture D balloon telescope, which is going to have a coronagraph on it to fill in potentially either, that's doing a test flight in October, so potentially looking at some of these targets. I think their contrast limit is about 10⁻⁷, and then future flights.
Yeah, so 10⁻⁷ is interesting because that's exactly where you enter a new region of disk physics where the dust is tenuous enough that its structure is dominated by dynamical effects rather than collisions. So that's already pretty interesting. After that, the key thing for exosody is the inner working angle. You can see it in this plot on the left. If you are north of 0.3 arcsecond, there's very little you can tell about habitable zone of nearby main sequence storage. So, yeah.
Thanks.
So one thing that hasn't been discussed yet are cosmic rays. They've been a nasty surprise for JWST, and I anticipate them being a major contributor to the error budget, but one that doesn't get talked about very much. So can you give us some insights?
I guess I'll go. With EMCCDs, we had an issue because the EMCCD is a CCD, and so in the serial register, you end up with a streak, and that gives you a big drop in efficiency. But that was very nicely mitigated by sort of a modified version of the EMCCD. Other sensor technologies that don't do that would obviously do better. I think with the narrow channel, just staying under 100-second, total frame time, I think at least for us, worked fine. I think it will work fine for HWO as well. Yeah, so I don't see a huge problem with cosmic rays in that sense. If you mean it in terms of, let's say, ionization or damage or traps, that could be something that we need to study in detail later to see what the vulnerability to that would be, and that might be a deciding factor in the detector technology that we go with.
Yeah, I want to add that in addition to the detector's concern, we also look into optics that close to the detector, make sure that we pick materials don't have fluorescence. That's another factor we put in our error budget. I think that's a good lesson learned to carry into HWO because we're going to deal with even more challenges in the photon counting regime.
I'll ask one more question. And it's really for almost anyone on the panel, but we have heard a lot about the 10 to the 8th contrast, 10 to the 9th with post-processing. We've heard about ideas of model validation, of error budgets, of what it took to build it. But what I'm interested in is what are your thoughts about going to the 10 to the 10th level in terms of what are the important things that we need to do on test beds to make sure that, when we extrapolate, our understanding of things, and we look at some of these really creative ideas like, the AI-based post-processing, that we're not fooling ourselves, that there isn't some physics there that we're missing. So what would you prioritize in terms of demonstrations to really give us confidence that we can go that last order of magnitude? Well, I'm asking about the gap from Roman beyond it. Like, what things from Roman, do you think will, leave that gap that we need to demonstrate? Not necessarily with test beds, but with anything.
So I'll start. It's a good question. There's a question that everybody asking. The first thing is the telescope aperture. You saw from Bertrand that, the major limiting factor for Roman is the central obscuration of telescope. So we're happy that HWO, don't have that anymore. That's number one. Number two, there are a number of additional limiting factors we're looking to. One thing in my mind is the chronograph mask quality. We use deformer mirrors and the masks to suppress starlight. They all have their own jobs to do. The errors from the telescopes and optical beam trains include reflectivity, including phase. Optics have polarization errors, have chromatic aberrations, but the DMs, with control two surfaces, have very limited capability. So that requires some of the masks to handle, for example, the chromatic aberration, make sure that that's not limiting us. And some of the chromatic masks at the focal plane are very tiny, so require very precise nano manufacturing. So these are the things, we put in the technology plan. That's, the, Bokar show is 3x3. That's a top investment, priority. Hope that we will get the money to do that.
Yeah, maybe one more answer to that, which is, so in that bag of anything that could happen between 10⁻⁸ and 10⁻⁻⁻, one effect is polarization. And so, and that's one that we cannot measure from the ground because it comes mostly from the primary and secondary mirrors. So that's one thing we look forward to validating in space on orbit, which is, with the whole assembly, the telescope and the chronograph behind it, what's the effect of observing in dual polarization? And that's going to be our only opportunity to validate the polarization aberration models and then use them, as you know, for HWO to decide whether or not we can split polarizations and whether we need to come up with polarization aberration correctors and things like that. I think that's going to show up at 10⁻⁹ level.
Thank you, everybody. I do encourage everybody to reach out to the panelists later today or in the 2 remaining days of the conference. Bertrand also mentioned the Roman white paper call. So before the end, I would like to ask all panel members, one by one, to tell us in about 30 seconds or less, what would you do if you had 10 hours of Roman observing time? Fun?
Oh, you want to start with me?
Yeah.
With 10 hours, the HW1 of top technology is ultra-stable telescope to show we are able to maintain optics, single-digit picometer. Roman provides a perfect opportunity. Remember, CGI chronograph has the picometer wavefront sensors in. Once we're in L2, very stable environment, we point the telescope to a bright star, turn on the low Zürich sensors, measure stability of the telescope, and timing is also perfect. We'll be launching Roman by end of next year, so 2027, 2028 is a perfect time to show that.
Perfect. So stability. Scott.
I'll tell you what I could do with 430 days of Roman time, but otherwise I don't think you want me to have 10 hours of chronograph time, so I'll pass on.
So thanks to all my answer, but as a scientist, I'll say exactly the same thing as he did, except that I would point that at a bright star of scientific interest, not just a reference star, so maybe Vega or Altair. And I would put a Wollaston prism at the back end to see the polarization effects at the same time.
Rana, 10 hours or any arbitrary other number?
I'm going to assume the engineers have done their thing, and I'm going to go for science. So I mean, I think if it's performing at its best estimates, and we have suitable targets that fall in the working angles, as much reflected light as possible, and then if that's not available, then I'd be interested in going after some of the self-luminous ones that we've detected in the near-infrared, but seeing them at a different wavelength range that we haven't seen before.
Thank you. Bijan.
Given that ExoZodi is going to dominate as error. And even at the 10 Zodi limit, it's going to vastly dominate, be the dominant source of integration time. I would donate my 10 hours to go deeper on those candidates.
Alice.
Yeah, I'll take 4 or 5 of Faint's 10-hour observations so that I can build a database of chronograph performance as a function of pitch angles and row angles. And then from this information, we can help the community figure out if there's a way to improve the control system, to improve the ConOps, so that the observatory can be more stable and provide additional model validation data for our engineers so that we can learn how to predict our performance better.
Excellent. Thank you. Before we thank our panelists all together, I do want to come back to the white paper call for Roman. So this is a chance for all of you to submit your ideas. So this was not just a question to animate the panelists, which I'm sure have a lot more ideas. I really want to point out that the Roman chronograph will not have a tag, and this white paper call might be your only opportunity to submit ideas for observations with the Roman chronograph. The August 7th deadline is a hard deadline. However, the template is short. It guides you through with answers not applicable, so NA is a valid answer. You don't have to overthink what you're putting in there, but please do put your idea in there and submit it. So get your ideas in. We really want to make sure that we make use of this very unique in-space testbed as best as we can in order to prepare for AHW. So big thank you for all of the panelists.
Thank you for such an interesting panel, and that concludes this afternoon's session. So let's thank all of our speakers again. And if you could stay with us for a few minutes, we have just a few announcements. So today is the last day for the day 1 and day 2 posters. And so if you've been presenting a poster, if you could kindly take that down before the reception this evening, we'd appreciate that. And if you have a poster for day 3 and day 4, if you could put that up first thing in the morning to make sure that participants can go review them. A reminder that the posters, that a digital copy of the posters are available through the conference website. So you can go there if you didn't get a chance, or if you want to follow up with some of the presenters, I encourage you to do that. We have a reception this evening, and Don Gelino was going to say a few words about the reception. Please.
Thank you, Mike. Hi, everybody. As Mike said, my name is Don Gelino. I'm the manager of NASA's Exoplanet Exploration Program, and I'm located at JPL. And so underneath the EXCEP program is the NASA Exoplanet Science Institute. And so some of you early career researchers are here because you got travel support. That was thanks to either the funds from the EXCEP program from NEXI or from NASA headquarters through Julie Crook. So, so I hope you're enjoying the conference, and please make the most of it. Okay, the reception. There's a reception tonight at 6 o'clock, so in a little bit less than 30 minutes. It will be up on floors 8 and 9. We want to thank the sponsors that I think you'll be hearing from, starting at 6:30, Lockheed Martin, L3Harris Technologies, BAE Systems, and Northrop Grumman. And so there is a roughly 30-minute gap between now and when the reception starts. We're asking folks to kind of stay in the lobby area or on the 4th floor. If you are on the 9th floor, stay there. I'll tell you why in a minute. Let's see, because they'll be doing some setup and stuff on floor 8. So please don't go there before 6 o'clock. Okay. So in that time, you can go look at posters, assuming they're still up. I know people are supposed to take them down by 6 o'clock, but you can wait until 6 o'clock to do it and then head to the reception. Or you can go, you can network, or you can go outside and get some humid air. I don't know. I've lived in Southern California too long. I had to take a taxi here this morning. I couldn't deal with it. Okay, and I like walking. Okay, let's see, what else? Okay, the important part, drink tickets. So everybody will get 2 drink tickets. There will be LOC folks located near the elevators on both the first floor, which is the top exit entrance up there, and B1, which is this middle one here. There will not be anybody down here, so if you go out this door, you need to go up a level, at least one level, to get your drink tickets. Get them before you go upstairs. If you are on the 9th floor in the overflow room, hello, and stay there. If you haven't already, if you haven't gotten them already, somebody will be up there to give them to you. So you can stay there, you can stretch your legs, you can come down if you want, you can, whatever. Remarks will begin at 6:30, and it doesn't matter if you're on the 8th or the 9th floors. The reception is on both floors. There are a lot of us. We can't cram it. We don't want to cram everybody in. The last thing I have to say is I'm chairing the session tomorrow morning. Please remember, we'll start promptly at 8:30, even though I know people are going to have fun tonight. So try to remember to come back and be here at 8:30 tomorrow morning. We're going to talk about astrobiology, which is super cool. All right, and that's it. So everybody have fun tonight. Thanks.